Welcome, everyone, to PALS. This is September 24th seminar. Today's speaker, Charlotte Ayton, who is a postdoc at Boulder these next 3 years. And her talk is Higher Dimensional Book Spaces.
Oh, hi everyone. Oh, okay. Hi everyone. Oh, still getting.
It seems, is your mic on your laptop? Oh, there might be. Because there's a room mic. You can.
Oh, okay, we're good. Okay. There's no feedback anymore. Thank you. So hi everyone. I'm happy to be here. This is, I think, my fourth talk for PALS, but it's the first one where I'm actually here at Boulder and am one of the organizers officially. So thanks so much for having me again. So. Today, I'll be talking about this project that I actually, what I'm going to be sharing, I actually basically did during my second year of grad school, which was a while ago now, but I took quite a while to post this. So the preprint just appeared on the archive on Friday. And so if you don't know what book spaces are or why we would care about higher dimensional ones, that's perfectly fine because that's what I'll be explaining in the talk. Let's see if I can. Okay, here we go. So I'm going to show that for n greater than or equal to 2, there exists some infinite family of compact n-dimensional simplicial complexes, which can carry the structure of topological modular lattice, but not topological distributive lattice. And well, I am going to assume that you know what modular and distributive lattices are, but in case you don't know about topological lattices whatsoever, that's fine, because that's what the talk is going to be explaining. So. And I'll also explain why this is interesting as well. So first, I'll discuss topological lattices just in some generality, and then I'll talk about their geometric realization, which is going to give us a bunch more examples than the sort of obvious ones that we'll have at the start. Then I'll talk about Walter Taylor's book space result, which is the two-dimensional version of the n-dimensional thing that I'll talk about today. I won't do it in too much detail by itself because I'm going to give an n-dimensional generalization of it, and so then you can recover Taylor's result from that. But I will mention that. And as I said in the, well, okay, and then I'll do the higher dimensional version, as it says there. And as I said in the abstract for this talk, the way that I got into this was in 2018, I went to a conference in Hawaii, and Walter was there. And I'd actually never met him before, but I knew that he, had some work at the intersection of universal algebra and topology, which I found interesting. And he gave a talk on this two-dimensional result that I'll mention later on, and asked one of the questions he asked was, are there any higher dimensional examples of the same kind of phenomenon? And well, in this talk, I will give those higher dimensional examples. And so it is basically the same techniques, but there is a little bit of work to make sure that everything goes through in higher dimensions. Okay. So, well, this first definition is kind of a lazy one. This is along the lines of, telling students that, vector space is a module over a field. We can have a model of lattice theory in any category that we want with finite products. And so a topological lattice is a model of lattice theory in the category of topological spaces. But if that's not already a familiar type of thing to you, then you don't want to think of it that way. But before I tell you a more down-to-earth definition, I'll tell you that examples include the real numbers with the usual ordering, the usual meet and join being like min and max. And we also can take intervals, like the interval between 0 and 1, closed or open, if we're just concerned about having a lattice, don't care about the bounds. Or just take any lattice and give it the discrete topology. That's the laziest kind of example, which means that every lattice that we're familiar with is actually also a topological lattice in this lazy way. Even the real numbers are, although it wouldn't be the same topologically. So a better definition, perhaps, is that a topological lattice is a structure which has a set, some topology tau on that set of elements L, and a meet and join operation so that L equipped to that meet and join is a lattice, and both meet and join are continuous maps from L squared to L. And what I mean by that is that L squared has the product topology induced by that topology tau. So this is the proper notion of a model of lattice theory in the category of topological spaces. I guess you could say with respect to the monoidal structure given by the product, but let's not go there. This is this is the natural definition of a topological version of lattice theory. Oh, and I guess interrupt me if there are any questions, or I can't see the chat, but let me know if there's any questions in the chat, please. Oh, you do have a question. Okay.
Oh, can you say that if meet and join are continuous, does that mean the lattice order is a continuous order, like in the sense of as a relation?
Yeah, so there is a formulation of so yeah, so you can, yeah, I think I want to say the answer is yes. So it's like if you use the topology that's induced by, I think, upsets or downsets, that you will have that the isotone maps with respect to that, or the continuous maps on the corresponding topological space. So there is a more intelligent way to translate, say finite lattices. But that's actually not the correspondence that I'm going to be talking about a little bit later. But that's a reasonable question.
Right.
Yeah. Well, okay, we'd like a way to produce more examples of these besides, there is the type of example that Chase just mentioned, but then also we could take products, subalgebras, and so forth in the appropriate category. We have to be a little bit careful about what the correct notion of taking the product or taking a subalgebra should be to preserve the topological aspect, but we can do those things. We would like a way to make new things that aren't just coming from doing these standard constructions to the ones we already know. We would like some more examples. And so one way to do that is by geometric realization. And so, I'll have you think about what I'm going to do with this lattice pictured here, which is otherwise known as M3. So it's modular, but not distributive. And, of course, I'll end up saying you can do this thing that I'm going to describe with any finite lattice, but let's think about this one for something concrete. So if we have some function, no notion of topology at first, just some function from the elements of L to the closed interval between 0 and 1, I'll say that its S level set is all of those elements of the lattice with the property that F sends them to something which is at least S. And so I'm going to say that a function is L admissible when each of these level sets is a principal ideal for any possible choice of S. And so this puts a little bit of structure on what F has to look like. And in fact, you can describe it completely for any given finite lattice by just examining a finite collection of conditions that this gives you. But I'm actually not going to explicitly do that here, but you can sit there and figure out what F has to look like, as a tuple, if you'd like to think of it that way, for any particular finite lattice that you choose. So, because there are only 5 values to consider, right? We just have to consider F of 0, F of A1, F of A2, and so forth. And this is going to give us some kind of condition on how those values are related to each other. Okay. So the geometric realization of L is going to be the subspace of 0, 1 to the L power, consisting of all of those L admissible functions. So the closed interval between 0, 1 has its usual topology. If L is a finite lattice, then by the 0, 1 to the L, I just mean the appropriate, size of L dimensional cube. Like for instance, I guess it would be the 5-dimensional cube for this example. And we can inherit the subspace topology from that cube. And so the order on 0, 1 to the L, as in I'll take the partial order that's induced by taking the product of 0, 1 with itself, use the closed interval from 0 to 1 with itself a bunch of times. That actually does restrict to a lattice order on the geometric realization as I've defined it. There's a little bit to check there. It's not nothing, but the meet and join operations that come from that lattice order are continuous with respect to the subspace topology that comes from the cube. So that was all done before. I'll give you references at the end, but that's known. So if I do the geometric realization of that modular but not distributive lattice M3 from before, I'll get what's pictured here. Now, due to my perhaps limited capacity to draw pretty pictures on the computer, you'll still have to use your imagination a little bit. I'll ask you to use your imagination even harder later on when I draw things that can't be embedded into 3D space. But the idea here is that, and I'll point at this for the people in the room. Each of these, there's sort of three triangles. So the lighter one and this lighter, smaller triangle in the middle being where they overlap. There's these three triangles, and each of those triangles comes from the geometric realization of one of the three maximal chains in this lattice. So each of those maximal chains gives us a two-dimensional triangle. And the idea is that these maximal chains would be two-dimensional simplices in the order complex of this lattice, for those familiar with the order complex of a poset. So I haven't really explained how that correspondence takes place, but I claim that that's where it comes from. And so this is an example of one of these book spaces that Taylor had discussed in his work from 2017, where we can think of each of these triangles that correspond to one of the maximal chains as being a page, and there's this spine which corresponds to the two-element one-dimensional chain from 0 to 1. So you can still imagine the bottom of this is 0 and the top of this is 1. There's this spine where these three triangular pages are all joined together. And so with a suitably liberal definition of what a book is, this looks like a book.
That's a 3D picture.
Yeah, so it's a 3D picture. I can't actually, so it's a 3D picture. So there's no, the overlap is from our perspective. We can't actually draw this properly. So it's like a book that has three pages and they only meet at that spine that is just a one-dimensional spine. And so we can do the same thing with any finite lattice L. Actually, also from 2017, George Bergman has a paper on similar things, and he discusses several infinite generalizations of this kind of construction. I don't need to go there in this talk, but you can do similar things with infinite lattices, but I'm going to just stick to finite lattices. And this isn't like necessarily obvious, but this is the same space as the geometric realization of the order complex of the lattice. And so, I'm not going to put up a rigorous definition, but what I said before is basically the idea. The usual geometric realization of a lattice from topological combinatorics would have us start with a lattice like this and say, we're going to make a simplex in our abstract simplicial complex for every chain, whether it's maximal or not. And so when we do that, well, in this case, we'd have three maximal chains, which would correspond to three triangles in the abstract simplicial complex, and there would be an abstract one-dimensional, line segment, which is the chain consisting of only 0 and 1, which is the place where all of these triangles meet each other. And so that's like the picture that I drew before. So we have a separate notion of geometric realization of abstract simplicial complex, which doesn't have any reference to the lattice structure. And so, so you might ask why didn't I just say form the order complex and then take its geometric realization, since that was familiar. But unfortunately, those don't give you the coordinates that you want. If you try to, and I'm also not going to write this down, but I'll just say it. If you try to take the convex combinations of the elements of the lattice that you're starting with and try to extend the meets and joins by assuming that those operations are like bilinear, that's sort of the obvious choice, right? Like forming the group ring. That won't give you a lattice structure. That will just fail to produce a lattice structure. So you can't do it that way. But there is this alternative way that I've presented to put a lattice structure on the geometric realization. So unfortunately, life isn't that easy. So in 2017, Taylor gave a family of two-dimensional compact simplicial complexes, which had the structure of modular lattice, but not distributive lattice. And I'm meaning that in the sense of topologically. So of course, we can find, if we ignore the topology, we can take any set with the cardinality of the reals and find a distributive lattice structure on it if we want to. But this is a more interesting question if we're asking to respect the topology of the set, because, of course, if we have something the size of the reals, we can just take the reals and be done. But this is a different question. And I'll remind you of this a little bit later, but I'm actually going to say something stronger than what you might first imagine, which is that I'm not going to just give you an example of complexes that are topological modular lattices, but not topological distributive lattices. I'm going to actually show, which is directly generalizing the two-dimensional result of Taylor, that actually these spaces cannot be endowed with a topological distributive lattice structure. So even if you chose a different ordering, different meet and join that somehow happen to be continuous, like in principle, like that's possible to do, but you can't do it in such a way that you respect the topology and also get a distributive lattice structure, even though these do allow modular lattice structure, as I'll show. All right. Oh, and then, as I mentioned before, Taylor asked whether higher dimensional examples exist, and the answer is yes, and that's what this talk is about. So basically, what I need to do in order to take what Taylor did and extend it to higher dimensions is I just need to add this I feel like there's got to be slang for this, but it's now escaping me. I just need to add this chain to the top. I just need to add this sort of little whisk coming off of the top of the lattices that Taylor considered for his book spaces. So what Taylor had done before was considered lattices that looked like this, where instead of having this B1, B2, B3, we just had one at the top there. And so and then we had just a bunch of atoms, A1, A2, A3, whatever. And so those are like a generalization of the lattice, the familiar lattice M3, which is modular but not distributive. And while those would all give two-dimensional simplicial complexes because the maximal chains would all have three things in them. And so that would give us two-dimensional triangles. So if we do the same thing, but we choose some dimension D and make sure that our maximal chains have D plus one things in them so that we get D-dimensional simplices from them, then, well, we can obtain something that gives us a higher dimensional analog of the book space. And I'll have a picture in a minute, but again, you'll have to use your imagination harder because it's not going to even be something that I could produce in 3D accurately if I wanted to. But yeah, so I'm not going to write down a proper definition, but just take the chain that has D plus one things in it and then replace its sole atom with N different things. And that's the lattice MDN. And so M54 is here. Okay. So all of these lattices are modular, but they're not distributive if N is greater than 2. And so to see that they're not distributive, well, 0, B1, and A1, A2, A3, which would be in any of these MDNs as long as N was at least 2, that's going to be a copy of M3. So it's not distributive, but I put it in the preprint, but it's an elementary argument that you can't have a copy. You can't have a copy of N5 inside of this thing. This is modular. So the geometric realization of these things are always compact D-dimensional simplicial complexes, as I've probably convinced you by saying that, the maximal chains determine the simplices, and there's only a finite number of maximal chains. And so what's pictured here, which takes a little bit of work to actually understand what you're looking at, but I did try, is the geometric realization of this M. This would be M32. Oh, sorry, 3, because it has three of those atoms in it, and it's well, has maximal chains of size 4, so 3-dimensional. And so this thing also is like 3 pages that are joined at a spine with a suitable definition of page and spine. And so by that I mean, and I'll maybe try to indicate with my cursor here, there's this two-dimensional triangle that appears here in the middle. That is like the spine. Because it's a 3D book, it's now a 2D spine. And if you look, each of these peripheral points out here corresponds to one of our atoms, A1, A2, and A3. And we have three-dimensional simplices, which all meet exactly at this two-dimensional triangle. And so if you maybe if you ignore the back simplex first and try to just imagine the two tetrahedra meeting at the triangle, you can imagine that. And then you can imagine gluing one more onto the triangle that is the spine, the two-dimensional spine of this three-dimensional book. And so it goes for more pages, and for higher dimensions, we can do the analogous thing and glue a bunch of n-dimensional or a bunch of d-dimensional simplices along a d-1 dimensional spine to make what I call a d-dimensional book space with n pages. And so, the reason that this is a little bit hard to picture is that probably intuitively, if you're trying to picture it at this point, you see that you can't actually have this in R3, right? This is you can visualize it by viewing how the pieces glue together, but unless you claim to be proficient at visualizing higher dimensional space, you're not going to be able to actually do this without picture it without self-intersection. Yeah, so that's actually not just an idle observation, but that's actually an important fact for the proof that I'm going to sketch in a little bit. And I want to point out that the analogous fact that Taylor observed in 2 dimensions was that if I have this 2-dimensional version of this, where I have 3 triangles that meet along a single line segment, that this doesn't embed into R2. So of course we can picture it easily because we can picture it in sitting inside of R3. But this doesn't embed into R2. You can flatten 2 of the pages down onto the plane, but when you try to insert the 3rd one, there's no way to do that without overlapping with one of the other pages. I mean, somewhere other than the spine, of course. So that same phenomenon was the important thing there. And so I always wanted to have a porism in one of my papers. I'm not sure. People have different ideas of what a porism is supposed to be exactly, but I think it's some kind of geometric proposition, some kind of geometric lemma or something like that. And so here's mine. When n is at least 3, the book space, this gamma MDN does not embed into RD. And so remember, n is the number of pages. And so it's saying if you have a book with more than, with 3 or more pages, then it won't embed into the natural choice for, Euclidean space to embed it into. Okay, and so I'll give you some indication of the argument here. So I'll first, well, this isn't much of a story, but I'll tell a little bit of a story. So as I said, I had basically done this back in 2018 when I was a grad student, and at the time I had looked at an argument actually that Taylor had given in correspondence to George Bergman, and then that appeared credited to Taylor in Bergman's paper of the same year. And it said that we could use invariance of domain in order to prove this. And if you don't remember what invariance of domain is, that's okay, because I'm going to tell you that I didn't end up using it anyway. But I at the time back in 2018 had told Walter, I think I can do the same kind of argument because invariance of domain works for higher dimensions too, and I believe that this makes sense. And then I went back this month and looked at my own notes and wanted to make sure that I was prepared to post this paper and give this talk. And I discovered that I couldn't remember exactly why I thought that it worked. And I'm now not sure whether I understood something back then, which I no longer understand now, or whether I was just wrong. But that's okay, because I think I have an elementary argument which doesn't need anything from algebraic topology. So, and it's probably what you would intuitively, think would make sense. And I think that this is a rigorous argument. So, okay, so if maybe let's look at the picture of the 2D one first. So if we think about 2 pages from this 2-dimensional book with 3 pages, 2 of those pages would make a square. right? And we believe that the square can be embedded into R2. And there's nothing weird going on with the topology of this either, right? When it gets the subspace topology from some Euclidean space, it's going to have the topology you would expect. So we can put 2 of the pages into R2, no problem. But then consider a point that's right in the middle of that square that's made up by those 2 pages, the thing right in the middle of the spine. That point is a limit point in this book space of a sequence of points going from the say the peripheral point of the 3rd page, whatever one you thought of as the 3rd page, there's a sequence of points that has that center point as a limit point. But if I have an embedding of the square into R2, then that center point gets sent to something with a neighborhood that is entirely inside of the square. There must be some radius epsilon around which everything that's within epsilon of that point is in the square. So there's no way that that sequence of points coming from the 3rd page could have that middle point as a limit point in the image in R2. So we have a problem. Either the map that we chose is not an embedding because it's not injective, or this is just a contradiction because it doesn't preserve the topology. We should have sequences of points that have something as a limit point, having a continuous map preserve that, right? So it's impossible to embed this into R2. So for an exactly analogous reason, if I imagine 2 pages of my 3D version of this thing, the 2 pages would be 2 tetrahedra that meet at a single triangle. And that thing is a closed ball in three dimensions. And so I can embed that into R3. But then if I do, there's going to be a center point, which is the middle of the 2-dimensional triangle that is the spine, where again, there's a sequence of points that come from the 3rd page, which has that center point as a limit point. But by an exactly analogous argument, there should be some radius around that center point inside of R3, where everything around it, everything close by, is inside of those first 2 pages. And so it's the same argument in higher dimensions. It's impossible to embed this into R3. And in general, if you have at least 3 pages, you can do the same thing. You can't embed the book with at least 3 pages into RD if it's D-dimensional. All right, so I believe that is a rigorous and more elementary argument than the one that I now no longer understand, and I'm not sure if I did before. Okay. So that was the porism. And now I have 2018 crossed out because I feel like I want to mention that I did do this a long time ago, but now it's finally been posted in 2024. I know the year doesn't really matter that much, but I don't know. These spaces admit the structure of modular lattice, but not distributive lattice when n is at least 3. And so I'll sketch the proof. So these lattices are actually subdirect powers of the corresponding finite lattices, MDN, via these maps that take a given admissible f. Remember from our definition of the geometric realization as these functions f that give us, for all of their level sets, we have principal ideals. We can actually take one of those admissible maps, and we can take it to the join of that corresponding principal ideal, which would just be the element at the top of it because everything's finite. And so this map actually turns out to be a lattice homomorphism, and these maps actually witness that this gamma MDN is a subdirect power just as a discrete lattice. Like without these aren't going to respect the topology. It's not gonna respect the topology because these maps are not constant, and if we put the obvious topology on the finite thing and made it discrete, then we're not going to have something continuous. So I'm not making any statement about the continuous structure here. I'm just saying as a lattice in the classical sense, gamma MDN, the geometric realization, is a subdirect power of just copies of the original discrete lattice. That means that every identity that those book lattices MDN satisfy, the book spaces with their natural lattice structure also have to satisfy. So because the MDN are modular, the geometric realizations all have to be modular, again, with respect to the natural lattice structure that I indicated before. and for which I didn't give you a formula for computing meets and joins because I don't need to get into it to prove this to you, and it's kind of a whole thing. All right. So that shows you that we can, well, because I claimed that the meet and join are continuous though for the geometric realization, that shows that I can have the structure of topological modular lattice on these book spaces. And it's sort of the natural one coming from that geometric realization. Well, these lattices are not distributive because they actually have a copy of these non-distributive things inside of them. So that with the natural notion of meet and join that I indicated before, coming from the ordering on the cube, these things are not distributive. We can witness that they have a failure to be distributive. We can identify elements of the original lattice with certain elements of the geometric realization and just see that the same, that the identity fails to hold. So I'm actually making a stronger claim here, though, which is that no choice of continuous lattice operations on these spaces, as long as n is at least 3, no choice of continuous lattice operations can make this space into a topological distributive lattice. And so this is also a direct generalization of what Taylor did. Taylor had used this fact, which was already known, and I'm now not remembering the reference actually, but Taylor had used this fact that if you have a d-dimensional simplicial complex and it carries the structure of a topological distributive lattice, then it actually has to be embeddable into RD. But Taylor just used it when D was equal to 2, but it's true in general. And I actually don't yet know the proof, but I believe that the idea is that in such a complex, you will be able to choose D points that determine the values of everything else. And so you can use that in order to explicitly construct an embedding into RD. But I don't actually know the details yet. So our porism said that these simplicial complexes don't embed into RD, so there's no choice of continuous lattice operations on it that can be distributive, because if there was, then it would contradict this other result, which is known. Yeah, so about the hardest work that we did, given everything else that was already known, was just choosing an appropriate choice of finite lattice, and then actually being able to see that these lattices don't embed into the corresponding Euclidean space. All right, so I think, okay, before I give you my references, I want to make a couple comments. So first of all, I think that this is interesting because it shows that dimension isn't really necessarily a factor that forces identities to hold or not hold for topological lattices. Like a priori, we might imagine that for higher dimensional objects, this type of thing cannot occur, and we may be forced to model certain identities by the higher dimensional space, even though a lower dimensional one wouldn't be forced to do so. But that doesn't seem to be the case here. So, which is, I imagine, is somewhat why Taylor asked this question of, can we do this in higher dimensions? So the higher dimensional simplicial complexes neither force us to model more identities or obstruct us from modeling identities in these cases. Well, that's, yeah, so I mean, I think that's one thing that's interesting. I think this subject is interesting in general because it's actually been known for quite a while that topological lattices are in general homotopically trivial. So if you think about all the examples we've seen, all of the examples of spaces I've talked about here have either been contractible, so having just the homotopy type of a point, or I mean, I guess I mentioned some discrete spaces, but those are homotopically trivial in the sense that every you choose a base point, you're going to have something with a homotopy type of a point. And so it's actually known that has to be the case. And so you might think, based on even like the work of Walter Taylor, for instance, from 2000, he has a paper, Spaces and Equations, where he gives some generalizations of the old well-known results on H spaces to other types of spaces, saying, okay, if you have a space that has this kind of cohomology that has this homotopy type, then it can't carry certain types of certain types of algebraic structure, you might think, well, this probably is a purely homological or homotopical thing, but that's actually not true. And lattices are a very strong example of it because different homeomorphism types of spaces will carry certain lattice identities, but not other ones. But up to homotopy, this is all trivial. So these obstructions, like the one that I discussed about being embeddable into RD, they're really geometric or topological obstructions, and you can't just reduce it all to, to homological algebra or algebraic topology, which I do like, by the way. It's just that there's more to life than it, and here's an example. Yeah, so I think that this is, so this is also interesting in that perspective that we can say, okay, so the homeomorphism type of the space matters, but does the dimension matter? And well, here, we've seen at least that it's possible for the same phenomenon to occur in higher dimensions. And so now, like, one direction for going forward would be to say, can I find equations that are forced to occur for simplicial complexes in dimension D, but not D plus one, for whatever given D. So that's perhaps another direction to go. And so, yeah, I just think it's really neat that, despite this being in some sense an elementary type of thing to ask, we've known that we can have models of certain types of algebraic structures in various categories for a long time. We actually still have a lot of detail that we might want to fill in about exactly what are the obstructions to having to modeling various kinds of identities. And as we can see, it's not only algebraic topology, although that can help us in some cases. So yeah, I feel like, oh yeah, there was one other thing I wanted to say, which is that these definitely aren't the only lattices that you can do the same kind of argument with. I didn't really have to replace the sole atom with a bunch of new elements. I could have just as well had this anti-chain be placed at any height, and I would have had the exact same arguments. That everything will still go through. So there are definitely many other choices to explore, and I hope that I've inspired some other people today to look into topological lattices a little bit more. So I'll just leave you with a few references. You can see there's a preprint on the archive. The two 2017 papers of Bergman and Taylor that I mentioned are here. And I also mentioned Taylor's Spaces and Equations from 2000. Thank you so much.